So today we'll be seeing about the controller design for enhanced variable speed and torque performance of PMSM motor for automotive application using direct torque control method. So first of all, permanent magnet synchronous motor uses the pair of permanent magnet that will be used to produce magnetic field, and the magnetic field interfacing with the rotor coils produce rotation in the rotor. And it is the permanent magnet synchronous motor is known for its compact size, and it is mostly used in electric vehicles and industrial machinery. So the problem in the current PMSM motor is, despite all the recent progress and current designs of PMSM motors, that continues to encounter concerning issues in efficiency, torque fluctuations, and operational range constraints. So our objective of this project is to improve and optimize torque performance for improved efficiency and operational versatility. So first of all, we need to come up with this project. We need to understand direct torque control technique and the simulation that we need to be doing, and how methods to reduce torque ripple by testing and mapping other parameters. Then we'll be designing the circuit for motor controller. So the signal flow graph will be like similar to this, and initially we'll be having a speed reference in the outer loop and torque and flex reference in the inner loop. So we'll be using a PID controller to stabilize the input, stabilize the feedback systems, and in this we'll be using a space vector pulse width modulation, which actually splits the voltage vectors in 8 voltage vector forms, out of which 6 are non-zero and 2 are zero vectors. The 6 voltage vectors will be splitted across 60-degree phase angle, and with that a pulse width will be generated, and the pulse width generated will be transmitted to the inverter, and the three-phase supply will be modified based on the pulse width by the inverter, and it will be controlling the PMSM motor. So the methodology that we have incorporated during the development of this project is, first we'll prepare a mathematical model for PMSM motor, then the model of PMSM in Simulink using mathematical model, then equivalent circuit is being designed for the PMSM motor. Then after the successful modeling of PMSM, we have created a model of torque and flux estimator blocks, and we have also made Park and Clark transformation blocks, which are actually going to be converting the voltage vectors in voltage into vectorical forms. And we have also designed the PID controller to stabilize the current, and we have also made the iterative process to find out Kp, Kd and Ki values. So, and model a converter block to calculate other parameters like speed and voltage. Estimating these parameters are actually more important. Then combining all these blocks, we have modeled DTC. Then finally we have iterated this process to n number of times and reduce the torque ripple as much as possible, and obtain desirable results. So this is the simulation that we have done in the Simulink model. So first we'll be we have made a supply voltage of 400 volts with 60 amps battery, and we have used an universal bridge inverter, and this universal bridge inverter gets the input of the pulse width in the form of G, and this pulse width is an output of the voltage DTC controller block. And we'll be using a PMSM motor which has a base requirement of torque as 90 Newton meter, and the measurement block actually converts all the speed and voltage vectors and phase current, and with all those we have mapped the speed and torque characteristics, and we have obtained graphs as. So the graph, initially the speed as a time graph actually initially rises above 800 rpm in the 0.5 seconds, then it actually increases to 1000 rpm, then it stabilizes after 1 second. The reference speed is actually about 950 rpm, and then shift to 1500 rpm. The speed drop is due to because motors usually operates with a certain power range, and the power is usually a product of speed and torque with along with some coefficients. So when there is a need to be maintaining the torque or increase in torque, so obviously we'll be having a reduced speed. So the torque versus time graph shows us that the torque ripple actually reduces after 1 second, and the torque stabilizes to 90 Newton meter as the desired torque that we have initially set. Initially, the torque required to overcome the inertia is actually higher, that is about 120 Newton meter. Then after a second, it stabilizes to 90 Newton meter. Thank you.